To this, excuse me, the bearing capacity for shallow foundations is a little analytical, not a little, it's a lot of uh, quite analytical. But what you need to know is just know the equation and how to apply the there are certain factors there which are either on a table. There's also a formula you can use to get them, but normally you're just given a table which you can read. So that's all. Once you know the basic formula, you can read some constants, and then you know about c and phi, then you are good. But we'll go through the entire derivation so that you are competent. But at the end, what is important is you can apply the equation and get the constants from the table and use them. Okay. Uh, at the very least, you should be able to derive the bearing capacity formula. So I try to go very slowly. If you have a question, ask, and of course, based on the just based on the principles that you should already know. So we are saying that the lowest part of a structure is generally referred to as foundation. It is a function. Its function is to transfer the load of structure to the soil on which it is resting. A properly designed foundation transfers the load throughout the soil, excuse me, without overstressing it. Overstressing the soil can result in excessive settlement or shear failure of the soil, both of which cause damage to the structure. So every material, if you think about it, if you apply loads beyond its capacity to carry it, of course it's gonna fail, and that's what we are saying here. So if uh, our 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 material here is soil, so you need to make sure that you don't overstress it, and when you overstress it, of course it's going to destroy the foundation, and also mm, destroy the structure. I'm sure you have done structures and their limits for settlement. For example, if you have a structure here, there, that's your support, this is your support, and there is some differential settlement such that excuse me, such that the beam maybe ends up like that. If this is a beam, from your structures you can calculate the stresses, but this is we don't need this. This would induce a lot of stresses in the beam, and your beam might fail. And this is what we are trying to say, that you should take care of the foundation such that the settlements are within reasonable limit, such that the structures are not destroyed. So depending on the structure, the soil encountered on various foundations are used. And on the soil encountered, various types of foundations can be used. Figure 1. So let's see figure 1. So this is the figure 1. You can use pile foundation, pile, but this the choice depends on the type of soil. So mostly if we have clay that is very weak, soft clay, then you go for piles. Soft clay, not soft clay alone, soft clay but very heavy material, heavy structures. Or if you have a good foundation but the structures are heavy, like traffic load, or the pier, the bridges probably on Thika Super Highway, and the bridges on the Nairobi Expressway. So probably the foundation is good, but then the loads are massive. Still, you need you can use pile. So we are saying figure 1 shows the most common types of foundation. A spread footing is simply an enlargement of load-bearing wall or column that makes it possible to spread the load of the structure over a large area of the soil. In soil with low bearing capacity, the size of spread footings required are impractically large. In that case, it's more economical to construct the entire structure of a spread concrete pad. This is called mat foundation. So, actually, what we're trying to explain here is that uh, you need to spread. The idea is that if there is weak soil, for example, what causes problems is what we call punching shear. Punching shear. Punching shear, the simplest way to put it is akin to the reason why if someone pricks you with a thick and sorry a thin or a sharp or a pointed thing, it will prick you. That's the punching shear. That's the idea actually. The reason why the doctor, when they try to give you an injection, the tip of the is it a pin, the whatever they are using to inject you, the syringe, and that is able to prick or enter your bloodstream because of the punching shear, that ability to punch. So this is a problem for our foundation, because if you have weak soil here, probably this is a layer of soil, but is very weak. So that means every time you put something, probably like soft clay. Let me try to use a different pen. If you apply soft clay, it will sink and cause a problem. So what we need to do sometimes, of course, if it is possible, we need to uh, spread the load to a wider area, because probably if you put foundation here, there might be excessive settlements around, such that your structure collapses. So what you need to try to do is spread the area, because you are saying the stress that the soil will feel is sigma over the area, I mean the load. So to reduce the sigma, class rep, to reduce this value, what do you do from this formula? Anyone? To read?
You increase the area, now
Yes,
reduce the.
but the load is fixed. The building of the structure, if it's 8 story, you cannot do anything about it. So the only thing you can do is increase the area. So that's why that's the idea of mat foundation. So you can extend, use a larger area, such that so when you increase the sorry so when you increase the area, when a goes up, sigma goes down. This is your point. So that's actually the idea of mat foundation. But you do not have limitless space, because also it's a question of space. For example, if you have plots, if if the boundary of your plot, like in Nairobi where you have plots there, and this is another another person's property, another person's property, and probably this is another person's property. Sorry, another person's property. You people, I believe you live in Nairobi, So if this is your property and then you require, and of course, maybe there's also another guy up there and down here. And normally you want to make maximum use of your plot. So if this is soft clay, probably you might need a mat probably that extends into your neighbor's uh, property, which we cannot. That cannot happen. You don't have that space. You cannot encroach into your neighbor's property. So even spreading the foundation or increasing the area, as so to speak, has its limits. So the mat foundation is good for soft soil, but when you have the space. Otherwise, if you don't have the space, then you cannot do that. But anyway, the idea is just to spread the foundation of a larger area so that you reduce the stresses experienced by the soil. So pile and drilled shaft foundations are used for structures when great depth is required. When great depth is required for supporting the load, piles are structural members made of either timber or concrete. Something is not right here. Just a minute, I figure out. Okay, so the piles are structural members made of timber or concrete or steel that transmit the load of the superstructure to the lower layers of the soil. According to how they transmit the load into the subsoil, piles can be divided into two categories: friction piles or end bearing piles. Uh, so, so what we are trying to say here exactly is that friction piles carry the load by, for example, so if this is a pile,
We have lost the screen, huh? The screen, can't see the screen.
is frozen or what? I think it's a
Yeah,
function.
it's
Now and now? Now?
No, I can't see it. The rest you can just confirm whether they are seeing from there, and I can refresh my device here. But from my end, I can't see it.
Anyone else who can't see? Class rep. So, what should I do?
Me, I can see from my end.
You can
I
see
can
the
see.
screen.
Yes.
Okay. Class rep, is your problem solved? Class rep? Class rep, did you solve your problem?
Yes, I've refreshed. I've refreshed.
Okay. So friction pile means that it carries because this is the soil. Friction pile means the main load carrying mechanism is through the friction uh, on the side. The load carrying mechanism is just by friction. Now then we have mm, so we have friction piles and end bearing piles. So for end bearing piles, the load carrying mechanism is that the load is carried by the end here. But actually, in fact, in reality, it's a combination of the two mechanisms. In reality, usually the load carrying mechanism is a combination of the two mechanisms, including the skin friction, uh, both the skin friction and end bearing. Anyway, we will do this in details when we talk about piles. But for now, you should know that the mechanisms for load carrying when it comes to piles, whether we have skin friction or end bearing. But in fact, most cases it's the two combination of skin friction and end bearing. So pile, I think already I have talked about that. In case of friction piles, the superstructure load is resisted by the shear stresses generated along the surface of the pile. In the end bearing pile, the load carried by the pile is transmitted to the tip to a firm stratum. In the case of drilled shafts, a shaft is drilled into the subsoil and is then filled with concrete. Metal casing may be used while the shaft is being drilled. The casing may be left in or may be withdrawn during the placing of the concrete. Generally, the diameter of the drill shaft is much larger than the pile. The distinction between piles and drilled shafts becomes hazy at approximately 3 meters in diameter, and definitions uh, nomenclature are inaccurate. Anyway, what we are saying here, when you are boring the piles, when you are digging the piles, because the hole is unstable sometimes, depending on the soil, I mean the type of soil or the type of material you are doing the excavation. So you usually put a casing, a casing. So this casing, after to keep the wall stable, then you can maybe bring your pile there. Eventually, put your pile. Once you fit your pile, so this is your pile, then you can remove your casing. You can leave the casing, in which case you're increasing the strength of the entire system, and the strength of the load carrying capacity. But actually, when you're doing the calculation calculations, you do not uh, take care of the casing. So you can either choose to remove the casing, withdraw, or leave it after construction. That's up to you. That's all we are trying to say, such that if you're seeing the drawing in plan, in plan this would be your casing, and then closely there, this is your pile. So you can choose to remove the case casing and your pile. So you can choose to remove it after the construction or not. So that's what we are trying to explain there. So spread footings and mud foundations are generally referred to as shallow foundations, whereas pile and drilled shaft foundation are classified as deep foundations. In a more general sense, shallow foundations are foundations that have em- uh, depth embedded to width ratio of approximately less than 4. So if you want to know the distinction between shallow foundation, uh, excuse me, shallow foundation to with deep foundation, then we are talking about, if this is your foundation, so you talk about the length, if you will, and the depth. So if d over l is less than 4, then you have a shallow foundation. Otherwise, you're talking about deep foundation. So also note, we are talking about spread footings and mud foundations, and even strip footings. Spread footing is strip footing, spread footing, uh, the same thing. But so those are called, even pad foundation. Those are called shallow foundations. But piles, when you come to piles and shaft, then those are deep foundation. If you want to know a distinction, then you check the ratio of the length to the depth. Then if the depth of a length is greater than 4, then we are talking about deep foundations. If depth of a length is less than 4, then we are talking about shallow foundations. So we will discuss about the shallow foundations as mentioned before. Uh, for foundation to function properly, you have to control settlement, and the soil and the settlement caused by the load must be within tolerable limits, and the shear failure of the soil supporting the soil must not occur. We use principles of compressibility and consolidation, and this is something you should have done. Class rep,
Yes,
have you done consolidation? All this you should have done.
it's in next term.
What do you mean?
It's under foundation.
Elasticity, theory of elasticity and consolidation. You should have done in some of the previous courses anyway. So this chapter introduces load carrying capacity of shallow foundations based on criteria of shear failure in the soil. Question? Any question before that? Any question before you get into the details?
I think we are okay.
Okay. To understand the concept of ultimate load bearing capacity and the mode of shear failure in soil, let us consider the case of long rectangular footing with B located in dense sandy layer or stiff soil shown in figure 2a. when a uniformly distributed load of Q per unit area is applied to the footing, it settles. If the uniformly distributed load Q is increased, the settlement of the footing gradually increases. When the value of Q gets to QU is reached, then that the bearing capacity of the soil, then at like the value Q equals QU, that's what we call the bearing capacity of the soil. It's gonna become clearer when we look at the photo. So imagine this. This is stiff soil. So we are increasing this load. This load goes up until this uh, until the soil here fails. At the failure point, this value Q becomes equals to QU. That's what we are saying. So if you are to draw the settlement, the actually this is how to test the piles also. It's also difficult to define the the load. I mean the failure. The point of failure is quite difficult to quantify. But we think that if you draw a curve of settlement, what you can see here. But let me draw a different another one there, such that if you have the load, and this is settlement S. Let's just say settlement S. So while you're increasing the load here, while you're increasing Q, you expect a curve there, there. That's what you expect, because when you increase, you expect the loading to increase. I mean the settlement to increase. So when settlement increases, uh, uh, at the point where there is a rapid increase of settlement, actually this is the point where punching failure occurs, because you can see settlement, the gradient is almost 90 degrees. So this can be defined as QU. That's what we're trying to do here. You can refer to this figure. So you increase Q until punching occurs, such that settlement increases uh, almost uncontrollably. So that is defined as KU. That's what the QU. That is what we are trying to say. Now remember, there's a general shear failure, and so just know for now that pay attention to this. So this we are talking about general shear failure, where that value increases to just QU. But local shear failure, they're all shear failures, and this value is that. Okay. So two things: there's general shear failure and uh, and local shear failure. You should note that the QU for local shear failure is less than QU for general shear. I mean, sorry, for yeah, general shear failure. Now, don't worry, because what's the difference actually is just the area. General shear failure affects a larger area rather than more than the local shear failure. So, but the behavior is more or less the same. Question, class rep?
No, no, no. I'm
Not
good.
yet. Okay. Any other person with a question? Okay. Now, so uh okay, the last statement was bearing capacity. So bearing capacity failure occurs. Though if you lost, you can connect here. QU. So when you are saying Q equals QU is reached, that's failure. So bearing capacity failure occurs because you can see the settlement is increasing too much. It's like you have lost the strength. The shear strength has been lost, and then there's no more strength. So there's the foundation is just sinking uncontrollably. That's what we are saying. So bearing capacity failure occurs, the footing undergoes very large settlement, that's what we were saying, without any further increase in Q. The soil on both sides of the foundation bulges and uh, surface slip surface extends to the ground surface. The load bearing capacity relationship like curve already shown in figure 2b. In this case, QU is defined as the ultimate bearing capacity. Okay, the bearing capacity of the capacity failure just described is called generalized shear failure and can be explained with reference to figure 3 when the foundation settles. So assume what we already assumed before now. So the settlement, you can see the settlement occurred as already, the settlement has already happened. So the assumption here is that because this will cause a will cause failure of a wedge, a triangular wedge. So this is zone 1, zone 2. But like we said, the soil surface will bulge, and actually it's assumed that in a logarithmic uh, this is assumed to be a log spiral. This is Terzaghi. Terzaghi assumed that that's a log spiral. So on both sides. So note the zone 1, zone 2, and zone 3. Okay. So yeah, so this is, I think this is modes of bearing capacity failure. A, generalized shear failure, and this is localized. So the two things we are talking about. So I said generalized shear failure is on part A, affects a larger area, and this is local shear failure. So, and that's why you can see the loadings are not the same. This affects a larger area, that's why it's higher than the local shear failure. So far I think that should be quite straightforward. Should be straightforward. Class rep, I'm giving you time so that it sinks in because we are going to get into mathematics. This is log spiral. So that's clear, right? Ella? Ella? Ella?
Hello.
Is clear up to there, right? The general shear failure and local shear failure.
Yeah. It's clear. It's clear. You are breaking a lot.
Yeah, it's the internet.
Yeah, it's the internet is hearing we are going to maths and is trying to break a lot, and when we want to concentrate.
Yeah, but so far I need, like, what you need to get is the principle, the idea, so that it's very clear when we get into the maths what we are doing. So uh, the application of a load on triangular wedge shaped zone marked 1, this area marked 1, and is common for all on all the is pushed down, and in turn it presses the zones marked 2 and 3 sideways. So this zone goes up and then pushes the side this and that sideways, this and that sideways. Okay. uh and then upward. So Of course, it will cause after it pushes sideways and then they will go up and causes what we call heaving. Heaving. Okay. So actually, this you have done. This you should have seen somewhere. If you punch, if this is a soil, and then you punch some, you'll see this part of the soil bulging like that. I think you can confirm this happens a lot in uh, in reality. So this is the assumption of Terzaghi, which was later assumed found to be quite reasonable, although also has its own issues. We will talk about all that in detail. So at the ultimate pressure Q, the soil passes onto a a state of plastic equilibrium, and failure occurs by sliding. If the footing test is conducted instead in loose to medium dense, so we are talking about stiff soil, but now we are saying instead, if this is done in loose to medium sand, then the load settlement relationship, like the curve 2 in figure 2b, occurs. So firstly, we have described the generalized shear failure. Now we are saying because when we assume soil is stiff and when they are loose, they behave differently. So now we are describing the localized shear failure. So please note, this is in stiff soil, and this is in loose to medium dense soil, that is why, that is what explains the differences in behavior. So when you design foundation, first you need to determine whether the soil is stiff, whether it's loose, because that will determine whether you use the formula for a generalized shear failure or local shear failure. If the soil on site is stiff, then you will use the formula for generalized shear failure. If the soil is loose, you should use the formula for local shear failure, because that is the most likely mode of failure. So then we are saying, if the footing test is conducted instead in a loose to medium in loose to medium dense sand, the settlement relationship is like curve 2 in figure 2b. So this is already shown here. Yeah, here. So this is, so we are talking about this part, the local shear failure. This is what we are saying now. So beyond a certain value of Q equals QU, the load settlement relationship becomes a steep inclined straight line. In this case, so just to make it different from the other, we refer to it Q prime is defined as the ultimate bearing capacity of the soil. This type of soil failure is referred to as local shear failure, which we have already talked about in figure 3b. This is the figure. So the key you should take home there is that when soil is stiff, we expect generalized shear failure. When soil is loose to medium dense, then we can have local shear failure, and that determines which formula to be used. The triangular wedge shaped zone marked 1 below the footing moves downward, but unlike generalized shear failure, the slip surface ends somewhere inside the soil. Some signs of soil budging are, however, seen. Yes. So it's not very clear for local shear failure. There would be some signs of bulging still, but this log spiral surfaces end somewhere within the soil because the soil is loose and not very stiff. Okay. So I stop there with the introduction. We start the mathematics in the next lesson. Question?